The dream of traveling among the stars has ignited the human imagination for centuries. Long before we had the technology to even leave Earth's atmosphere, visionaries painted vivid pictures of distant galaxies and alien worlds. But it wasn't until the 20th century that science began to catch up with these far-reaching fantasies. The modern era of space exploration began with a historic milestone in 1961, when Soviet cosmonaut Yuri Gagarin became the first human to orbit the Earth. This achievement didn't just represent a technological triumph, it was proof that human beings could survive, adapt, and work in the unforgiving conditions of space. Gagarin's orbital flight laid the foundation for the decades of exploration that would follow. A few years later, the Apollo program would catapult humanity even further. The legendary 1969 moon landing, where Neil Armstrong and Buzz Aldrin walked upon the lunar surface, wasn't just a victory in the space race, it was a monumental step for humankind. These first human steps on another celestial body marked a bold declaration: we had the ambition and ability to reach beyond our home planet. As we entered the 1970s, NASA's Voyager 1 and Voyager 2 missions expanded our horizons even further. These twin probes, launched in 1977, delivered invaluable insights into the outer planets and the edge of our solar system. Both spacecraft now drift through interstellar space, carrying with them the golden records, time capsules with sounds, images, and messages from Earth, created in the hope that intelligent extraterrestrial life might one day find them. The Voyager missions didn't just gather scientific data, they symbolized our willingness to venture beyond known frontiers. They offered a glimpse into the vastness of space and a tangible sense of what interstellar travel might look like. But humanity is not one to remain static. As we pushed deeper into the cosmos, the need for better propulsion systems became evident. Traditional chemical rockets, though powerful, have serious limitations in terms of fuel efficiency and travel duration. That's where ion propulsion comes into play, a game-changing innovation in space travel. Ion engines, like those used in NASA's Dawn mission, represent a major leap in how we navigate space. Instead of relying on chemical combustion, ion propulsion works by ionizing a gas, usually xenon, and then accelerating those ions with electricity to create thrust. This technique allows spacecraft to travel for extended periods using far less fuel, making it ideal for deep space missions. The Dawn spacecraft, launched in 2007, exemplified the power of ion propulsion. Tasked with exploring the asteroid belt, it became the first spacecraft to orbit two extraterrestrial bodies, Vesta and Ceres. Using ion engines, Dawn could enter and exit orbits that would have required prohibitive amounts of fuel using traditional rockets. The efficiency of ion propulsion allows for flexible mission planning and extensive exploration, even though the trade-off is lower thrust and slower initial acceleration. While propulsion technologies were evolving, our understanding of the universe was also undergoing a revolution. The discovery of planets beyond our solar system, exoplanets, transformed how we think about the cosmos. In 1992, astronomers made the first confirmed detection of exoplanets, two rocky worlds orbiting a pulsar. This discovery broke long-held assumptions and opened up an entirely new field of research. Then came 1995 with the identification of 51 Pegasi b, the first known exoplanet orbiting a star similar to our Sun. This gas giant, located around 50 light-years from Earth, proved that planetary systems like our own might be common across the galaxy. The floodgates opened, and since then, thousands of exoplanets have been discovered using various detection techniques. Among the most intriguing is Proxima Centauri b, discovered in 2016. Orbiting Proxima Centauri, the closest star to our solar system at just 4.24 light-years away, this exoplanet lies within its star's habitable zone. This means it could potentially host liquid water, a key ingredient for life as we know it. Its relative proximity and potential habitability make it a tantalizing target for future exploration and even the possibility of human colonization. The discovery of Proxima Centauri b was made possible by the radial velocity method, which detects minute shifts in a star's motion caused by the gravitational tug of an orbiting planet. This method has proven instrumental in the discovery of over 1,000 exoplanets, each one a stepping stone in our quest to find life beyond Earth. However, the greatest challenge in reaching these distant worlds lies in developing the propulsion systems capable of such voyages. Even our most advanced technology today isn't enough to traverse light years within a human lifetime. Take ion engines, for example. They are incredibly fuel-efficient and ideal for deep space missions, but they produce very low thrust. That means they can't be used to launch spacecraft from Earth's surface, and even once in space, they take a long time to build up speed. NASA's New Horizons mission highlights both the triumph and the limits of current spaceflight capabilities. Launched in 2006, this probe gave humanity its first close-up images of Pluto in 2015. Beyond Pluto, it continued into the Kuiper Belt, a region filled with icy remnants from the formation of the solar system. TO achieved the speeds necessary to reach Pluto in under a decade. New Horizons relied on a combination of chemical propulsion and a gravitational slingshot from Jupiter. This gravitational assist dramatically increased the probe's velocity, allowing it to cover over 3 billion miles in just 9 years. However, even at a blistering speed of over 36,000 miles per hour, interstellar distances remain daunting. To truly go interstellar, we would need technology that drastically surpasses our current capabilities. One of the most daring concepts ever proposed was nuclear pulse propulsion, first envisioned by physicist Stanislaw Ulam in the 1950s and later developed into the bold Project Orion. The idea behind nuclear pulse propulsion is stunning in its simplicity and power. The spacecraft would eject small nuclear bombs behind it, detonating them in sequence. A massive shock-absorbing plate at the rear of the spacecraft would absorb the force of each explosion, propelling the ship forward. Though it sounds like something out of science fiction, the physics behind it is sound. Calculations during the Orion project's development suggested that such a spacecraft could potentially reach up to 10% the speed of light, far faster than anything built before or since. At such speeds, a journey to Proxima Centauri could, in theory, be completed in a few decades within a human lifetime. However, political, ethical, and technical hurdles ultimately halted Project Orion. The Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in space, was a death knell for the program. Still, it remains one of the most ambitious propulsion concepts ever devised. In recent years, one of the most daring and futuristic initiatives aimed at making interstellar travel a reality within our lifetime is the Breakthrough Starshot project. This ambitious international scientific endeavor envisions sending a probe to our nearest star system, Alpha Centauri, and reaching it within just 2 decades. What sets Breakthrough Starshot apart is its novel propulsion method. Instead of relying on traditional fuel-based systems, it proposes using a light sail, an ultra-thin, highly reflective sheet powered by an immense array of ground-based lasers. These high-intensity lasers would bombard the sail with photons, transferring momentum and accelerating the probe to incredible speeds. Since this system doesn't carry any onboard fuel, it drastically reduces weight and, theoretically, could achieve up to 20% the speed of light. However, transforming this concept into a working reality isn't without massive challenges. For starters, the laser array required would need to generate an optical power output of about 100 gigawatts, roughly 100 times more powerful than the world's most advanced energy storage systems. Not to mention, the task of synchronizing around 100 million lasers to maintain a precise and focused beam on a minuscule sail millions of kilometers away is an enormous technical hurdle. To tackle these issues, scientists from the Australian National University have proposed deploying a laser-guide satellite. This satellite would assist in beam targeting and alignment, ensuring accuracy even as the probe races across interstellar space. Despite the daunting obstacles, the potential payoff is profound. Should the mission succeed, Breakthrough Starshot could transmit high-resolution images and scientific data from Alpha Centauri, offering humanity its first close-up look at another star system, and perhaps a habitable world. Although human travel to the stars remains decades away, robotic precursors may get there first. Intelligent AI-powered probes could autonomously explore distant systems and send back data without requiring real-time human intervention. One fascinating theoretical approach is the use of von Neumann probes, self-replicating machines that could mine raw materials and build copies of themselves at each destination. This would allow a rapid, exponential expansion of our reach into the galaxy without continuous Earth-based support. When humanity does finally take the plunge into interstellar space, concepts like generation ships or interstellar arcs may come into play. These massive vessels would host entire self-sustaining communities, complete with farms, water recycling, energy systems, and social structures. Multi-generational missions would allow human settlers to gradually migrate to distant stars even if the journey took centuries. Beyond Earth. While light sail technology holds immense near-term promise, researchers are also exploring more radical propulsion methods that challenge the limits of known physics. Among the most captivating is the warp drive, a theoretical propulsion system inspired by Einstein's general theory of relativity. Instead of moving through space, a warp drive would manipulate space-time itself, contracting the fabric of space in front of the spacecraft while expanding it behind. This effectively enables the craft to ride a space-time wave, traveling faster than the speed of light without violating the cosmic speed limit. Physicist Miguel Alcubierre brought serious attention to the warp drive concept in 1994, when he proposed a mathematical model showing how such a phenomenon could theoretically work. The main catch? It requires exotic matter with negative energy density, a substance that may not exist or is at least beyond our current means of production. Still, ongoing theoretical work keeps the dream alive. Another visionary idea is the Freeman-Dyson interstellar jet engine. In this concept, vast mirrors or lenses would capture the energy output of a star, focus it onto a spacecraft, and convert the intense energy into thrust. While the physics is tantalizing, the technological demands, including materials capable of withstanding and harnessing such immense energy, remain far beyond our present-day capabilities. But perhaps the most powerful proposed propulsion system is one based on antimatter. When antimatter meets matter, both are annihilated in a burst of pure energy, a reaction that could, in theory, provide propulsion at a fraction of the mass used. This makes it one of the most efficient energy sources imaginable. However, antimatter is extremely difficult and expensive to produce, and storing it safely is an entirely separate challenge due to its explosive reactivity. Nevertheless, antimatter research continues, driven by its unmatched theoretical potential. Interstellar travel is more than just a question of how fast we can go, it's also a question of survival, engineering, and resourcefulness. One of the greatest dangers is radiation exposure. The deep space environment is teeming with high-energy cosmic rays and solar particles that can damage both human tissues and sensitive electronics. Current shielding methods, while effective for shorter missions, won't suffice for journeys that could last decades or even centuries. To address this, scientists are researching new materials, advanced composites, and even magnetic shielding systems that can deflect harmful particles away from spacecraft. However, creating lightweight, durable, and effective shielding that doesn't compromise fuel efficiency or structure remains a critical obstacle. Then there's the question of spacecraft durability. Vessels designed for interstellar voyages must survive prolonged exposure to micrometeoroids, cosmic debris, and structural stresses over long periods of time. At the speeds envisioned for interstellar travel, even a grain of sand could cause catastrophic damage. To counter this, engineers are exploring reinforced carbon composites and modular spacecraft that can repair themselves mid-flight using onboard AI. Another challenge is maintaining life support, not just for robotic systems, but potentially for human passengers. Advanced autonomous systems will be required to monitor, maintain, and repair shipboard systems. Concepts like hibernation or suspended animation are being explored to reduce resource consumption during long voyages, but they are still experimental. The enormous costs associated with interstellar exploration cannot be ignored. Building, testing, and launching even a single interstellar probe would require a level of investment far beyond current space missions. Collaboration between governments, private enterprises, and international consortia is essential. Historically, space programs were almost exclusively funded by government agencies like NASA, Roscosmos, and ESA. But with the emergence of private giants such as SpaceX, Blue Origin, and others, there is a new wave of innovation and funding strategies. Crowdsourced science, global cooperation, and public-private partnerships may be the key to financing such monumental endeavors. The core of this entire pursuit is the search for another Earth. Among the most promising candidates is Proxima Centauri b, discovered in 2016. Orbiting the closest star to our solar system, this exoplanet lies in the habitable zone where conditions could, theoretically, allow for liquid water. Its proximity, just 4.24 light-years away, makes it an ideal target for exploration. To aid in the search for more such worlds, the European Southern Observatory (ESO) has installed a new, highly sensitive instrument on the Very Large Telescope (VLT) in Chile. This device enhances radial velocity measurements, improving our ability to detect Earth-sized planets by observing minute stellar wobbles caused by orbiting bodies. The VLT is currently focused on Alpha Centauri A and B, sun-like stars that could potentially host more planets within their habitable zones. These new tools might soon help us identify planets previously invisible to even our most powerful observatories. A significant leap came recently with the discovery of LHS 475b, an Earth-sized exoplanet located about 40 light-years away. Found orbiting a red dwarf star, this world has an estimated surface temperature of around 107 degrees Fahrenheit, suggesting conditions that could support an atmosphere, perhaps even liquid water. This discovery, made by NASA's Transiting Exoplanet Survey satellite, TESS, uses the transit method, detecting slight dips in starlight when a planet passes in front of its host star. During these transits, light filters through the planet's atmosphere, enabling astronomers to analyze its chemical makeup using transmission spectroscopy. Studying LHS 475b helps us understand why Earth and Venus, although similar in size, evolved so differently. It may provide insight into how atmospheres are retained or lost, especially for planets orbiting red dwarfs, the most common stars in the galaxy. In the ever-deepening night of our universe, where stars shimmer like scattered embers on an obsidian canvas, humanity finds itself listening, not with ears, but with instruments as sensitive as the cosmos is vast. Our yearning to know whether we are alone has persisted through millennia, from ancient myths etched on cave walls to the silent revolutions of data streaming through fiber optic lines beneath our feet. Now, poised at the threshold of discovery, the Breakthrough Listen project emerges as one of our most ambitious efforts, a cosmic sentinel tuned not merely to sounds but to the deliberate whisper of intelligence beyond Earth. Breakthrough Listen, launched in 2016, was designed not just as a scientific experiment but as a philosophical undertaking. With access to some of the world's largest and most sensitive radio telescopes like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, it scours the Milky Way for narrow-bandwidth radio signals, those elusive fragments of energy that may carry the hallmark of an artificial origin. Unlike natural cosmic radio sources, which tend to produce wideband signals, a narrowband signal, often less than 1 Hz in width, might indicate intent, precision, and intelligence. The stakes are enormous. In these whispers might lie evidence of civilizations that have risen, perhaps flourished, or even fallen before our species first walked upright, but the search isn't limited to the realm of radio. Optical telescopes have joined the hunt, seeking technosignatures in the form of laser pulses, brief, powerful beams of light that could cross vast interstellar distances with minimal dispersion. If an extraterrestrial civilization were to broadcast a signal deliberately, lasers would be an effective medium. They pierce through cosmic clutter with clarity, capable of being focused on distant star systems like an interstellar flashlight. The hope is to catch one of these flashes, not accidental, but deliberate evidence of someone, somewhere, sending out a beacon. The magnitude of this quest is staggering. Consider the Milky Way, a galaxy of over 100 billion stars, many of which are orbited by planets, perhaps trillions of them. The sheer volume of data is mind-bending. Yet, this is exactly where Breakthrough Listen innovates. Using advanced algorithms powered by artificial intelligence, it analyzes petabytes of raw data, seeking out anomalies. It sifts through the radio noise of the cosmos the way archaeologists dust off ruins looking for artifacts not of Earth but of thought, design, and pattern amidst entropy. While technosignatures are the focal point of Breakthrough Listen, the broader search for life has taken 2 main trajectories: biosignatures and technosignatures. Biosignatures are the molecular footprints of biology. They don't shout across space, they persist passively in the atmospheres of planets where life alters chemistry. Oxygen, for instance, especially when paired with methane, is a powerful biosignature. On Earth, oxygen is replenished by photosynthesis. Its continued presence in an atmosphere implies active life. Methane, too, while possible from volcanic activity, becomes more interesting when it exists alongside oxygen, which should otherwise destroy it. Their coexistence could indicate a balancing act of biological origin. The James Webb Space Telescope JWST, humanity's most sensitive eye in the sky, plays a vital role in this biosignature hunt. Using transmission spectroscopy, it examines the starlight that filters through the atmospheres of exoplanets during transits. Each molecule absorbs light in specific wavelengths, leaving behind a fingerprint. JWST's instruments decode these patterns, revealing the presence of water vapor, carbon dioxide, methane, and other gases. These patterns, delicate as they are, whisper of climates, chemistries, and perhaps biologies far different from our own, but the discovery of biosignatures, while momentous, doesn't confirm intelligence. They hint at ponds, forests, maybe even alien bacteria. Technosignatures, however, speak of societies. They hint at languages, technology, cities, and dreams. Imagine catching the glint of a Dyson sphere, a megastructure enveloping a star, capturing its energy. Such constructs, while still theoretical, could be detectable via their infrared waste heat. Or consider the possibility of detecting the flicker of city lights on a planet's night side, an uneven brightness unaccounted for by natural causes. These are not just signs of life, they are signs of purpose. The specificity of technosignatures makes them uniquely valuable. Biosignatures can arise from abiotic processes. But a narrow bandwidth radio pulse repeating every exact interval? That's not the language of volcanoes. That's rhythm, repetition, design. It's an artificial beacon in the natural wilderness of space. To improve the odds of detection, non-trivial decisions have shaped the Breakthrough Listen project. One such decision was to focus initially on nearby stars within a few hundred light years. Closer targets mean stronger potential signals. The second was bandwidth, scanning from 1 to 10 GHz, a relatively quiet part of the radio spectrum, often called the water hole because it lies between the emission lines of hydrogen and hydroxyl, the constituents of water. This part of the spectrum is assumed to be a logical meeting place for civilizations attempting interstellar contact. Yet, listening isn't enough. Interference from Earth-based signals, satellites, radar, commercial broadcasts can swamp even the most carefully tuned instruments. Machine learning models are now trained to distinguish potential alien signals from earthly ones, learning patterns that defy the randomness of natural emissions or human-made clutter. This separation of signal from noise is the heart of the quest. How do you detect a whisper in a thunderstorm? Even so, the silence persists. But silence itself is a message. It teaches us to refine our methods, to search more wisely. As technology advances, so too do our ears grow keener. New generations of telescopes like the Square Kilometre Array under construction in Australia and South Africa will expand our cosmic hearing tenfold. Yet, even with the most powerful instruments, we might miss the signals. Civilizations might communicate in ways we don't yet understand, using physics beyond our grasp. Or they might be listening, just as we are, hoping someone else makes the first move. Perhaps they've already sent signals, but those signals were lost across the eons, arriving before we built our first radios. Timing, as in all things, is everything, and then there's the possibility that intelligence evolves differently elsewhere. That what we call technology is a phase, not a destination. Perhaps other species evolve to blend with their environment, forsaking metals and radios for biological adaptation. In such a case, their technosignatures would not resemble ours at all. They might be hidden in frequencies we don't observe, or in forms we don't classify as signals. Still, we search. Because the question is too profound to leave unanswered. Are we alone? It's a query that transcends science and touches philosophy, art, and soul. To hear even a faint response from the stars would be to break the existential solitude of our species. And the quiet between transmissions we build. We build instruments that turn light into data, we train algorithms that see patterns we miss, and we dream of dialogues with civilizations long past or yet to rise. The universe is vast, but so is our determination. We have sent our greetings in golden discs aboard Voyager. We have carved radio messages into the ether. Now we listen. The night sky remains silent but not empty. For each star we examine, each frequency we parse brings us one step closer to the moment when the silence breaks and we hear, finally, the answer we've been seeking all along. And when that moment comes, should it ever come, it won't merely be a scientific triumph. It will be a turning point in human history, a cosmic dawn that redefines what it means to be alive in the universe. Until then, the search continues. And with every signal we decode, every molecule we identify, and every anomaly we catalog, we write a new verse in the epic of our celestial odyssey. Even as we amplify our cosmic eavesdropping with the most advanced radio arrays and signal processing algorithms, our gaze cannot linger solely within the Milky Way. We're turning our eyes outward to the grand scale of the universe, observing entire galaxies as potential beacons. The logic is both simple and staggering. An ultra-advanced civilization might not be whispering from a single world but shouting across light years, shaping their entire galaxy with massive engineering projects. Imagine Dyson spheres fully encasing stars or civilizations tapping the power of supermassive black holes. Such mega-engineering could leave signatures detectable even across intergalactic voids. This extragalactic SETI approach is bold. But it isn't easy. Distances are astronomically vast, signals become vanishingly faint. Telescopes require extraordinary sensitivity, and our data analysis pipelines must be smarter and more discerning than ever. Still, every galaxy we scan and every spectrum we decode brings us a step closer to the cosmic truth. Are intelligent civilizations unique to our galaxy or strewn throughout the universe? Enter the pioneering study led by Carmen Chosa and her team in 2023 using the Green Bank telescope. Over a 5-year period, they targeted 97 nearby galaxies, scanning 4 distinct radio bands between 1 and 11 gigahertz. This undertaking was not merely a technical challenge, it was a cultural and scientific milestone. Operating under the assumption that advanced civilizations might exhibit Kardashev Level 2 behavior, harvesting energy at a planetary system level, they deployed a potent weapon in their arsenal. The TurboSETI pipeline. TurboSETI is more than code, it's artificial intelligence tailored to detect narrowband signals that drift in frequency due to the relative motion of source and observer. But the battlefront is fraught with interference. Our own planet's radio emissions, satellites, radars, broadcast towers warp through every observation, mimicking or masking potential extraterrestrial calls. To mitigate this, Chosa's team alternated between observing on-source and off-source fields in thrice-repeated cycles. A true interstellar signal would only appear in on-source scans, while terrestrial interference would be present in both. It's a clever filter in a storm of radio noise. By the end of their campaign, the team had amassed a staggering 634,313 hits. That's 634,000 potential signals flagged for drifting frequency patterns. Advanced automated filters then pared these down to 1,519 top candidates. Each candidate was dug into, scrutinized by algorithms, then eyeballed by scientists hunting for telltale signs of alien engineering. The result? All candidates were traced back to earthly or natural origins. The echoes of pulsars, satellites, or ground-based interference. None carried the unmistakable stamp of alien intelligence. Does this feel like a setback? Not at all. Each null result is a lesson learned, a map that narrows our search. As machine learning techniques improve, older datasets can be re-examined. Signals previously buried under noise might emerge anew under revised algorithms. The frontier recedes but never vanishes. From searching the skies to mapping the solar system, our curiosity spans every scale. Take Neptune, the distant, iconic ice giant. Cloaked in what we believed was a serene, deep blue hue, this world has hidden surprises just beneath its tranquil facade. Our modern understanding of Neptune's color, atmosphere, rings, and moons has evolved dramatically since Voyager 2's 1989 flyby. The first close-up view of this 8th planet from the Sun, long depicted as a royal blue orb. Voyager's instruments detected Neptune's brilliant azure shades, but even these science-grade images required calibration, enhancement, and interpretation. These early hues gave us a canvas upon which we projected our assumptions of a tranquil, distant deity in the night sky. With the advent of the Hubble Space Telescope and the Very Large Telescope (VLT), astronomers began to paint a more precise portrait. Instead of the deep, uniform blue, new images revealed varied tints, muted blues, subtle greens, even soft grays, reflecting real atmospheric dynamics, not just our image processing. A groundbreaking study from Oxford University, led by Patrick Owen, added context by studying Uranus alongside Neptune. Over decades, they captured Uranus's changing reflectivity across seasons, using advanced spectroscopy to decode atmospheric composition, methane content, and aerosol behavior. Their careful back-and-forth calibration between Uranus and Neptune debunked the myth of Neptune's monochrome blue. Now, we know the color difference between the two giants is subtle, rooted in atmospheric particulate and methane variations rather than the dramatic contrast once assumed. More than aesthetics, these revelations speak to Neptune's turbulent nature. High-resolution monitoring shows swirling storms, most famously the Great Dark Spot, Neptune's counterpart to Jupiter's Great Dark Spot. Unveiled by Voyager, this storm was a massive, Earth-sized vortex carried by supersonic winds hitting 1,300 miles per hour, the fastest in the solar system. Seeing Neptune's atmosphere as calm? Now we know it's anything but. We've also detected blazing thermal hotspots in Neptune's upper atmosphere, measuring over 750 K, striking given Neptune's vast distance from the Sun. What generates such heat? Internal dynamics, variable solar heating, or magnetospheric processes? Theories swirl like Neptune's storms, but science has yet to pin down the exact mechanisms. Neptune's environment is even richer when you consider its family. Triton, its largest moon, holds secrets of its own. Sporting an odd retrograde orbit, nitrogen-rich geysers venting frozen volatiles, and a thin but seasonally variable atmosphere, Triton is far from inert. In 2000, its southern hemisphere warmed enough for nitrogen and methane ices to sublimate, enriching the atmosphere and revealing a climate driven by seasons that span half a human lifetime. Other moons, smaller but no less interesting, punctuate Neptune's rings, thin bands of ice and dust that trace the traces of lost satellites shattered by gravity. Neptune's rings are so faint that even modern telescopes struggle to image them, but in 2022 the James Webb Space Telescope delivered a crisp snapshot re-identifying dusty rings unseen since Voyager's passage. So what does all this mean? In asking about life in the universe, we embrace everything from the grandest galaxy-wide engineering projects to the faint telltale hues of ice giants a couple billion miles away. We search for technosignatures among the Milky Way and beyond, harnessing next-gen telescopes, AI pipelines, and ever-deepening databases. Simultaneously, we re-examine familiar worlds in sharper focus, correcting decades-old misconceptions. In the cosmic theater, every act, from the search for whispering radio beams in distant galaxies to deciphering the true color of an ice giant, adds clarity to our self-portrait as a species in search of meaning. Each failure spurs new strategies. Each image reviewed with new eyes refines our gaze. And with each passing year, we inch closer to the moment of illumination, when data becomes signal, noise becomes narrative, and a single discovery could shift our place in the universal story. Until then, we continue to listen and to look, beyond the Milky Way, across intergalactic voids, and back home to planets we thought we knew. Because in the boundless scale of the cosmos, even the faintest whisper or the smallest correction holds the power to change everything.